Good evening, students. Hope you're doing well. I'm also doing well. As you're seeing, econometrics class is progressing. We would have seen a number of things, right? Right now, I feel you're confident with the estimation part of beta 1, beta 2. You also know what is regression, basically. Then comes estimation, right? So we know what regression is. Like we saw in last class, when we see regression and when we have estimates, okay, using estimator. So estimator kind of a formula or methodology which we'll use to obtain estimates. For example, in a simple linear regression or a multiple linear regression, we use OLS estimator. Okay, like that we have got a number of estimators. Now, more important uh, about the model is whether the model is precise or not, right? For example, we have y and x, then we are using a regression model where we'll be getting estimates, right? So with the help of estimates, what we'll be getting is we'll be getting yi hat. We have actual values of y, and then the values of y which we actually get using the estimates. For example, if it is y equal to a plus bx, right? A is the intercept or the constant, and b is the estimate, and x is the x value. So when we multiply the coefficient with the independent variable, and then we add the intercept, what we'll be getting is we won't get y, we will get only y hat. So the y hat should be as much as close to y, right? Only then the model that we're using is trustworthy, otherwise it is not. So the precision of the estimate, okay, is very important, because otherwise we won't be using a precise model. So the precise model can be determined only by its precision. So now you see, that is why we are going for goodness of fit, right? Whether the model is actually fit or not. So R squared, or coefficient of determination, okay, is called a very good tool to test the goodness of fit. Okay, so now if you could see the PPT slide which I'm showing to you, here we have a basic regression equation as y equal to alpha plus beta 1x1 plus beta 2x2 plus the error term, right? So what here we are getting is, this is the expression of a dependent variable as a function of one or more independent variables, right? So this equation, regression equation, gives us the functional relationship between the dependent variable and the independent variables, right? So y depends on x1. So here we could say, since here there is linearity because we have parameter as well as we have the variables which have a linear relationship with the dependent variable. Why? Because you could see here the parameters raised to the power 1 as well as the variable x1, x2, and all, right? All are variables, right? They are raised to the power 1. So both have linear relationship. So if you could see in this linearity, what is the amount of change in which the x can influence y? Okay, so if x is changing by 1 unit, what is the change in y? Okay, so that is what is regression all about. So what is the average effect of x on y? On an average, we are saying. So when I say on an average, then we have regression line, right? The line that expresses relationship between y and x. Okay, so this relationship can be expressed only with the help of regression equation. So we have y and then we have x. So when we bring in both variables into an equation, so what we'll be getting is, we'll be getting the, depending on the number of independent variables, we'll be getting number of coefficients, right? Number of betas. And then we'll be having one intercept, right? So the intercept and the coefficients, and then we have values of x. So while incorporating the appropriate values, we'll be getting the regression line. So the regression line, it expresses the relationship between y and x. Okay, so here we'll be predicting y. We'll have actual value of y, and then we have predicted value of y. How come this y value is predicted? Okay, the alpha value, which will be getting, right, estimates. And then we have estimates of beta 1 and beta 2, right? And then we have the values of x1, x2. So when we incorporate all the values, we'll be getting the predicted value of y. So actually, regression line gives us the relationship between the predicted value of y and the actual value. Okay. Now it's important to test the goodness of fit. That is, how well the regression equation actually describes the relationship between dependent variable and independent variable. Okay. How well it is able to describe the relationship. How much of the variation in y is captured by x. Okay. If y is changing by 100%, how much that variation in y is captured by x, right? So that is what is all about goodness of fit, right? Now you see, so here, as we have discussed, R squared, that is coefficient of determination, it is determining, it is what is being determined, the relationship is being determined. Okay, so in what extent? The proportion of variation is explained by the estimated regression line. Okay, so we have y, we have actual values of y. So in actual values of y, we can see changes, because we have different values of y. For example, we have 2, 3, 4, 6, 8, 10. So we have got variations, right? So when we see 100% variation in y, taking into account all the values, then how much percentage of the variation is explained by the estimated regression line? And how we are estimating this regression line? By incorporating the values of intercept as well as the coefficient. So what we are doing, we are multiplying the coefficient value, that is value of the parameter in case of population, or value of sample, right? Statistic. So we have parameter or statistic. We can call them estimates. So coefficients, better word. So beta 1, beta 2, we are multiplying with x1, x2 values. And then we have intercept, and then we're adding to it. So in that way, what we're getting is, we'll be getting the estimated regression line. Okay. So how much percentage of the variation is explained by the estimated regression line? Okay. That is what is very important. When we see only R is nothing but the coefficient of correlation, right? It is not determination. It won't determine anything. It will just indicate the relationship between any two variables, that to any two continuous variables. That is very important in case of correlation. And we saw that it's called Pearson's correlation coefficient. We should have two continuous variables. Then only we'll be able to understand the linear association or linear relationship between any two variables. Now, coming to this R squared. So whatever coefficient of correlation value we are getting, and when we are multiplying that with the same value, R squared, what we're getting is the proportion of variation in y explained by the estimated regression line. So that estimated regression line is estimated in the first place using the values of x, right? So now what is this variation all about? What variation is explained? That will also here, variation refers to the sum of square differences between individual values of y and the mean value. So we have y, whether it is population or sample, right? We'll be having individual values. For example, we have 10 observations, then 2, 4, 6, 8, 12, 24, 28. Like that, we'll be having 10 observations. And then we can easily find the mean of it. Okay, in Excel or in normal calculation, manually also we can find mean. So we have individual values and then we have mean value. You find the difference of individual values and mean value. And then when you square it, okay? So square differences between the values of individual values of y and mean value. This is what is variation. And how much percentage of this variation is explained by the estimated regression line. So what we'll be getting, we won't be getting this actual value of y, we'll be getting yi hat. In the case of estimated regression line, as we know very well, we won't be getting the y values as such. We'll be getting more than the values of yi or lesser than the value of yi. They are called as yi hat, predicted value of y. So that value of y is predicted using the coefficients of the independent variables. So that is why the independent variables are able to have an effect on y, and how much of the effect is explained. Okay, how much of the effect is explained in the total variation. Okay, so if y is changing by 100%, how much percentage of the variation is explained by the estimated regression line or by the independent variables? So that is what is all about the R squared. Now you're getting it right. So this R squared is simply how we can define as it's a statistical measure that shows the proportion of variation explained by the estimated regression line. So when we use the word estimated, we directly mean that it deals all about the yi hat, not about simply yi. What is yi is the actual value and yi hat is the predicted value. And how that value is predicted is very important, using the coefficients and the intercept. What are the coefficients? Nothing but the parameters in case of population and statistic in case of a sample. So we have values of x, we have estimates, that is intercept as well as parameters. And then when we incorporate the values accordingly, whatever we are getting by the regression equation, we'll be getting this estimated regression line. Okay. Now, if I say variation, what is actually variation? Something but the sum of the, you see here, summation, right? So summation taking one value at a time, right? If it is yi, then y bar, then first value of y minus y bar, second value of y minus y bar, like you're taking one value at a time. So sum of the square differences between values of y and the mean of y, it is called as variation. So this variation is explained by the estimated regression line. If it is how much it is explained, whether it is explained 100% or 80%, that is various. If it is explaining more than 60%, we can say the model is good. Okay, because at least 60% of the variation in y is explained by the model taken up. If we are getting R squared as only 10 or 15 or 2%, then only 2% of the variation in y is explained by the estimated regression line, which is not good. So our model is not trustworthy. We have to include many variables, or some of the key variables have not been included in the model, or somewhere the data that we have used has gone wrong. Okay. Now, so when I was talking to you about the R squared, that is the total variation explained by the estimated regression line. So this is the estimated regression line. Okay. And now here we have yi. Okay. So here we have y bar. Okay. The mean of actual y values. And here we have individual y values, right? So you can see the line from yi to y bar. Okay. This is what is TSS, actual variation. Okay. Now we have this regression line. This regression line is able to explain, okay, for example, this is the actual y value, and this point is the predicted y value. So the regression line is able to explain only some part of the actual y value. Okay. The remaining part of the actual y value goes unexplained. Okay. So here the TSS, total, sum of squares, okay, can be said as explained sum of squares and residual sum of squares. Okay, so TSS is equal to ESS plus RSS, explained sum of squares and residual sum of squares. So what is TSS? We know it very well. It is the sum of the squared differences between individual yi value with that of the mean yi. Okay, mean of y. This is TSS. And this regression line is able to explain only some part of the TSS. That part which is explained is called as ESS. Now you see the ESS formula. So it is you see here. So TSS, total sum of squares, is equal to yi minus y bar whole squared. Right. Then summation of yi minus y bar whole square is TSS. If you look at ESS, you could see here summation of y hat minus y bar whole square. If I say y hat is nothing but the predicted value. So predicted values of y minus y bar whole square is ESS. Then what is RSS? In RSS, what we have is, we have yi, that is actual y value, minus y hat whole square. So summation of yi minus y hat whole square is RSS. So this is the regression line. It is able to explain only some part of TSS. That explained part is called as ESS, and some part is not explained, that is called as RSS, because our model is not perfect. That is why we have error term. In a regression model for specification, what we have seen, we have the dependent variable, we have independent variables, and then we have error term. What is that error term is all about? It's all about those variables which have not been included in the model. Okay, the effect of all those variables which have not been included in the model is represented by the error term. Okay, now you could see here, what is y hat? This is the predicted value of y given x. So given x, what is the predicted value of y? Then what is yi? This is the actual observed value of y. Then what is y bar? Is the mean of y. Okay, so now we are very clear about what is R square. R squared is the how much percentage of the variation is explained by the estimated regression line. So what is that variation is all about? It is all about the summation of yi minus y bar whole square. Okay, but here when we use the term regression line, which is estimated, there now we are not going to have the actual value of y, because the actual value of y cannot be estimated by any model, because even if you are going to use hundreds of independent variables, we will definitely have some error term. Okay, so the value y hat, which we are obtaining, may be close to y, but it cannot be actual value of y. Okay, that is very important. So now, how much percentage of the variation is explained by the estimated regression line is given by the ESS, and the percentage of variation, okay, which is not explained by the estimated regression line, is given by RSS. That's it. As the name indicates, explained sum of squares, that is variation explained, then residual sum of squares, the variation that has gone unexplained, right? Now you see what is RSS? The R squared, it always takes value between 0 and 1. So the closer R squared to 1, we can say the model is better, or the model is able to explain the relationship between x and y in a better way. Okay, so this expression, that is summation of yi minus y bar whole square, again actual value of y minus y bar whole square, is called as TSS. So TSS is nothing but the total variation of actual y values from that sample mean. So this is R square actually. So TSS is the total variation of the actual y values from that sample mean. Then ES is all about how much percentage of this total variation is explained. ESS. RSS, how much percentage or share of this total variation goes unexplained. Now, you see the formula. You see, the TSS can be divided into two categories. So TSS is equal to ESS plus RSS. What is ESS? Explained variation. Explained sum of squares or explained variation is the portion of total variation that measures how well the regression equation explains the relation between x and y. Okay. So you could see the formula here, summation of yi hat minus y bar whole square. So how much percentage of the total variation? Percentage or share, I'm using the word percentage because if you're expressing R squared, if it is 0.56, you always tend to express in terms of percentage. Okay, if it is 0.56 R squared, then you can say 56% of the model, 56% of the change is explained by the model. Okay, of change in what? Of change in y is explained by the model. Okay. So ES is about the portion of the total variation that measures how well the regression equation explains the relationship between x and y. Now RSS. You can see here, it is yi, that is actual value of y, minus yi hat, that is the predicted value of y. So summation of yi minus yi hat whole square. So this expression is called as unexplained variation. So it explains the portion of the total variation that measures discrepancies or errors between actual values of y and those estimated by the regression equation. So with the help of regression equation, we'll be getting the regression line. So the regression line shows us how much percentage of the variation in Y is explained by the model. So that is ESS. So if the variation is 100% and ESS is able to explain only 80%, it means what? The model has got some errors. Always it will be, the model will have some error. There is no doubt in it, because we cannot have, the actual value of Y over there, because we can at best include only key independent variables. We cannot keep on going, adding independent variables, because then we have other problems as well. We have, as we have seen in the classes, the problem with more number of independent variables, multicollinearity. Okay. At the same time, it is not possible for us to hit at the exact Y value, which is not needed at all. So we should have a robust model which could explain, a major share of variation in Y. That's it. So now we have RSS, that is residual sum of squares, unexplained variation. So in the portion of total variation, okay, if it is explained, it is ESS. If it is unexplained, it means what? It is RSS. That is, so RSS measures the errors or discrepancies. Okay, so errors and discrepancies that arise because of the gap between the actual Y value and the predicted Y value. Okay, so this predicted Y value, how it is predicted? It is predicted by the estimated regression equation. So the errors between the actual Y value and the predicted Y value estimated by the regression equation. So this is what RSS is. Very simple, right? So TSS, RSS, TSS, ESS, RSS, very simple. Now, so once you know about how to calculate ESS, RSS, and TSS, then we can do R squared. So what is R squared? Is nothing but the ratio of explained sum of squares to total sum of squares. So ESS by TSS, or we can use another formula, that is 1 minus RSS by TSS. So based on this formula, you can easily obtain R squared. Okay, and this R squared can never be negative. Why it can be negative? Because we have actual value of Y, because you see the definition of it. That is the sum of the square differences between actual value of Y to that of the mean value. Okay, so sum of the square difference between yi minus y bar. So yi will have value, then what we have is we have mean will have some value. Even for example, if the yi where I equal to 1, that is 0, right? Even if it is 0, it will have mean value, because we cannot have all the values of y as 0. It is not possible, right? Then we won't be able to run the model at all. So even if 1 or 2 values in y happen to be 0, what we are going to get is we'll be getting mean value, because some values will be 12, 14, 16. We have a mean value of y. So 0 minus, let us say 12 as mean value of y, 0 minus 12, and then we have to square it. So it becomes positive value, because summation of yi minus y bar whole squared. Okay, it is the sum of the square difference between the values of y with that of their mean. So it cannot be negative at all. So that is why the range of R squared is 0 and 1. Now, the coefficient of determination using ESS and TSS, you're obtaining what is ESS and what is TSS, and then the value comes to be 0.7941. So what it indicates, it means 79.41% of variation in Y is explained by variation in X. So how much percentage of variation in Y is explained by the regression model? So, or in other words, how much percentage of variation in Y is explained by X? So if it is 0.7941 into 100, so 79.41% of variation in Y is explained by 1. Okay, now you see the coefficient of determination cannot exceed 100%. It will lie between 0 and 1, because the R squared value always indicates regression line that can closely match the actual data. Okay, actual data will be matched. How much closely it is going to be matched? That's what we are going to see. Now we have seen R squared. Okay, so with the help of R squared, we are able to estimate whether the model is good or not, because as per the goodness of it, how much the model is fit. the model is here, we can say the model is really a good fit. Why? Because almost 80% of variation in y is explained by x. This is a very good model. But whether this r squared is significant or not, that is, so the significance of the r squared can be estimated using f test. Like we have individual coefficients, like in beta 1, beta 2, and all. So for us to estimate their significance, we are using t test. In this case of r squared, for us to obtain the significance, we can go for f test. So because they follow f distribution, like we have seen in the earlier classes. So the f test, okay, will have null hypothesis. What is null hypothesis? Regression coefficients equal to 0. So all the regression coefficients, that is, are equal to 0. That is, in other words, you can say the model has got no predictive capability. The model is not able to predict the variation in y. The model which you're using, you have got 10 independent variables, and then you're using, it is not able to predict the change in y at all. Okay, the x is not able to predict or capture the change in y at all. So all the regression coefficients are equal to 0. That is what null hypothesis is. Okay. Now, basically, what you're doing in f-test is you are comparing a model with 0 predicted variables and deciding whether the inclusion of coefficients, that is the parameters of statistics. Okay. So the inclusion of coefficients, whether it has improved the model or not. So we have independent variables and their corresponding coefficients. Now we compare two models, the model without any coefficient, that is only intercept, and the model with coefficients, because each independent variable will have coefficient. So now whether the inclusion of the coefficients has improved the model or not. So the assumption is all regression coefficients are equal to 0, or the model has got no predictive capability, right? Now, if the result is significant, how it can be significant? Because you'll be having a calculated f value and then you have a table f value. So this calculated f value should be more than the table f value. If it is more, then you can say that your model is significant, right? So here the f statistics, okay, can be obtained by, you see the formula ESS. You know how to obtain this, right? Summation of y I hat minus y bar whole squared. Okay, RSS, summation of yi minus y hat whole squared, then t minus 2. T is number of observations. Okay. So with this, you'll be able to understand what is TSS, what is ESS, what is RSS, and why does it matter? Because it's all about the R squared, goodness of fit. So how fit is your model? Okay. Whether you are including one variable or two variables or hundreds of variables, those variables should give the goodness of it. Okay. What is goodness of it here? That is, variation in y should be explained by the x, or the variation that is happening in y should be explained by the regression equation or a regression model or your estimated regression line. In whatever way you're trying to sum it up, the variation should be explained. If it is not being explained, then the model is of no use. How much time you have gone, you have put over there, or how many variables you are including, it doesn't matter at all. Okay. Now let us go to a practical part of it. Okay, I think this Excel file is visible to you. Okay, now if you could see, we have yi and we have x. Okay, now here we have to predict y value. Right? How will we be predicting? For prediction, what we need coefficients. Okay, and we intercept. We don't have intercept. We don't have coefficients. What will we do now? So what we can do is we can use the data analysis package in Excel. You'll be having all these things in your system, it seems. So regression, go for it, and then you select yi value, and then similarly you select x. Okay, and then label. Why label? Because you have selected label, right? Then output range, you can give some range over here. Okay, first you click over here and then give a range. Then you can also select this on residuals. Let us see. Okay. So now what we are getting is, if you could see clearly, we have intercept value and we have the coefficient of x. Okay. So now we know this regression function, which is y is equal to a plus bx. So for us to obtain y I hat, we have to substitute the values of the intercept and the regression coefficient in this format. Okay, so we have x, so we'll be having values of x. So a is intercept, which we have it over here, and then we have b, coefficient value, right? So the coefficient is over here, or the slope. Okay, so this will tell us. So what is the use of 0.15? We can interpret directly because we have a linear relationship or linear regression. So if x is changing by 1 unit, then y changes by 0.15 unit. So this is what slope is. So additional change in y to additional change in x. Okay. So as per the formula given here, what we can do is we can select this intercept. Okay. Then plus, what is your beta coefficient? 0.15. Okay. Then into the value of x. Okay. So now if you are dragging, you see we are getting zero values. We are getting, not able to get any values over here at all. Why? Because we're not fixing it. Okay. This beta B2, okay, the value of x changes, right? The value of x changes, okay. But the values of A and B should not change. They should be fixed. Okay. So we have to fix it. How to fix? For that, what you can do is you can type F4 in your keypad. F4. Use the key F4. So please keep the cursor over here and use the key F4. In that way, we'll be able to fix A as well as B, that is intercept, as well as the coefficient value. So beta B2, that is the value of x, should change. And now when you drag it, here we see, we have dragged it. Okay, and then we are able to obtain it. Now, what we are able to see is, so this is the actual y value, and this is the predicted y value, and this y value, which we have predicted using the estimated regression. As you could see here, the model is able to explain only, certain portion of y, but not the, entire portion of y. It is not being explained. Okay. Now we can use the formula. So we can now, find TSS, ESS, and RSS. And this is the mean value of y, right? So we can easily find mean value, average. So this is the mean value of y. So what is TSS? As here we could see summation of yi minus y bar whole square. So this is the y bar, right? And this is the individual value of yi. So 3.5 minus 3.5, So we have to square it, whole square. But we can track this. There is no need to fix any value over here. Yeah, we have to fix one value. What we have to fix? We have to fix this one, right? Because mean is same throughout the series. So just use F4 key. In F4 we are able to fix it. So once we are fixed, then we can drag it. So this is your TSS, total sum of squares. Then we have summation, right? Let us find summation. So sum. So this is your TSS. Okay. Then ESS. What is the form of ESS? Y hat minus y bar whole square. Summation of y hat minus y bar whole square. So this is your y hat. Then we have y bar. We have to fix this. As we know, y we have to fix, right? Then we are squaring it. Then summation. So you see, the total variation is 0.68, and ESS, that is using the regression equation, we are able to explain only a certain portion of TSS, that is 0.54. If it is 68%, we are able to explain only 54% of the total variation. Right? Now, what is RSS? Simply, we can say 0.68 minus 0.54 is RSS. Right? So it will be 0.14. Let us see whether we are getting it or not. So this, what is the formula now? Here we have y hat, yi minus y hat whole squared. So we have yi minus y hat. Okay. Then let us square it. Actual value of y minus predicted value of y. Then when you're going for sum of it. Good. So as simple as that, right? Okay. Now the thing is that, so this is the summary output of regression model. So using Excel itself, using this data analysis package, okay, we have got this summary output regression, okay, where we have R squared here, 0.79. Now, what is the formula of R squared, which you have seen? So R squared is equal to ESS upon TSS, right? So let us try over here. So ESS upon TSS. Here you go. So we can match, okay, whatever output we are getting using data analysis package, and manually also we are getting the same value. Okay. Now, more important than this, you look at this ANOVA table. In ANOVA table itself, what we have is SS, that is explained sum of squares, and then we have residual SS, that is residual sum of squares, and then we have total sum of squares. Okay, here you see this one. So we have residual sum of squares, 0.14, we have explained sum of squares, and then we have total sum of squares. Okay, and now look at the F value. F value is 23.14. Okay, then you can see here it is significant, 0.00. So it is significant at 1% level because we have the range, right? So 0.00 to 0.01. Now 1% level of significance, right? 0.011 to 0.05. 5% level of significance. Then 0.051 to 0.10. This is 10% level of significance. So here the significance of F value, it falls in the first category. Zero point zero zero to 0.01. So this is significant at 1% level. Okay. Now, how we are getting this F value? We can use the formula itself. Okay. What is the formula over there? The formula is ESS upon RSS, then T minus 2, divided by T minus 2. Okay. So this T is nothing but number of observations. Okay. We'll try. So we know what the ESS is. Okay. First, let us solve the denominator part. So RSS divided by T minus 2. So how many observations we have actually? Let us see. So we have count 8 observations. So first thing is the RSS divided by 8. Okay. Then this is the value in the denominator. So we have ESS divided by denominator value. We're getting 30.85. The formula is ESS RSS by T minus 2. Okay. So what we are going T minus 2? Okay, T minus 2, right? So number of observations minus 2. So it is 6. You know? Yeah. Now you see 23.14286. Yeah. Here we have 23.14286. Okay. Now the thing is that this is the estimated or calculated F value. We have to compare this with that of a table F value. In the case of a regression output, we are getting it ready-made, some kind of ready-made. We are getting that F value is significant. This model is significant. If this model is significant, then the 79.4% of variation in Y is significantly explained by the variation in X. Okay. But now, manually, how we can do? Okay, manually, what we can do is we can, obtain the table value of F. How come? Fi and V. Okay, use this in Excel, Fi and V. Okay, what's the probability? Let us go for 1% probability, right? So we can go for 0.01. Okay, then degrees of freedom. Here they are asking for 2 degrees of freedom. Over here, let us say 1. No, degrees of freedom is what we had. We had 6 now. Yeah, t minus to 6. Let us see, 1 and 6. 13. Okay, 13.74. Okay, so 13.74 is the table F value, and 23.14 is the calculated F value. So the calculated F value is more than the table F value, right? So we can say it is significant. This is 5%, let us see. Fi and V, probability 5%, 0.05, then 1, then 6, 5.98. Okay, this is 5%. This is 1%. Okay, so because we had a number of observations, right? So n minus 2, 6, and then we had only one parameter. No? So we have given Fi and V. Probability is 0.1. Then we had only one predictor variable. That is only one independent variable, 1. Then we have got to use 8 observations. So n minus 2, 6, 3.77. Okay. So we can reject the null hypothesis. Okay, that the model is not significant at all. Okay, at 1% level itself. That is why we can say that the model is highly significant. Okay. So with this, we are able to see how to obtain TSS, ESS, RSS, how to test the goodness of it. And once we are obtaining R-square value, how we can interpret. The interpretation is very important, right? How much percentage of variation in Y is explained by X, or is explained by the estimated regression line, or is explained by the regression model. For example, if here the R-square happens to be 0.794, it means 79.4% of the variation in Y is explained by X. Now, what is this adjusted R-squared? So what we are doing is we are adjusting R-squared to the number of observations and the predictive variables. So in some cases, if you use more number of observations, obviously R-square will be higher, but that won't be a proper way, for us to compare between the models. So if you are taking more number of variables, if you are taking more number of observations, those must be adjusted so as to get the trustworthiness of the model, so as to see whether the model that we are using can really fit, and we are able to obtain the total variation in Y or not. Is it really a fit model or not? Okay, so for that we have to use adjusted R-squared. Okay, when we are comparing between models, it is always better that we go for adjusted R-squared, because what is adjusted over there? The R-squared value is adjusted for the number of observations as well as the number of independent variables that it is. Okay, as you could see over here, so this is the formula of the adjusted R-squared. As you could see in denominator, the model, the R-squared is adjusted for n observations and k, the independent variables that you have taken, or the parameters that you have taken, because the parameter are part and parcel of the independent variable. Okay, if you have got 2 independent variables, and you're having 2 parameters, right? And then what is multiple R? Multiple R, it explains the relationship between the independent variable and the dependent variable. So if you have got x1, x2, x3, x4, so what is the combined relationship of the independent variables with that of the dependent variable? In case of simple correlation coefficient, which explains the correlation coefficient of Y and X, not even Y and X, because in correlation we don't have the case of dependent variables, any 2 variables. So what is the relationship between any 2 variables? Correlation coefficient. In the case of multiple R, it explains what is the relationship between the X variables that we have taken up and the Y dependent variable. Okay. So with this, we'll stop this class. Hope in this class, we would have understood how to estimate R-squared manually, and we can also compare that with that of the summary output that is easily obtained with the help of data analysis package. Okay. And we also understood the importance of F Even though R squared is the goodness of it, the F, it tells whether the model is significant or not. The R squared can be higher, like 0.98, 0.99. But if the F value turns out to be insignificant, then the model is of no use. So we have discussed in detail, it seems. It's really good to know all these things. Okay, now we know how to do it, how to estimate in Excel, as well as how to estimate practically using manual method. In both now we are very sure. Okay, so with this we'll stop. Thank you for your patience. We'll meet again.